started with the first session of the morning with an invited talk from Lenka Zdeborova from EPFL.
Thank you, Alex. Thanks, everybody, for making it here in the morning in a neuroscience conference, listening to somebody who never worked on anything in neuroscience. I will tell you my perspective on understanding learning with the artificial neural networks, and I hope this will invite you to think about the possible connections. So, as everybody is aware, AI made astonishing progress, and just like I Googled what's the IQ of ChatGPT, and I found that apparently 155, and that's about the same as Elon Musk or Einstein. When I chat with it, it does seem impressive. It does seem very impressive. But how was this success achieved? Okay, what happened? Like, what was the foundational breakthrough that allowed us that? It's kind of interesting. What drives the industry today is just making things bigger, scaling things up. So we took better computers, better GPUs, we made the datasets larger and cleaner, and we took the networks with more trainable parameters. And the kind of scaling laws sketched on the figure are driving, kind of, they are empirically derived, very predictive ways of how it will actually improve if we make it yet bigger. So, and it's all kind of empirical. It's amazing. So, but of course the drawback is that the cost, if your only kind of way to improve, a main way to improve is to make things bigger, then the cost is just driving it insanely high. So there are many fundamental things that we don't know. Like, for instance, the scaling. Is it really necessary? Can we do it otherwise? And, okay, you know better than I do that somehow brain seems to need less energy and less data to do a lot of these functions. And even on a much more kind of smaller level, like this DeepSeek startup in China, kind of shook the $1 trillion industry. Just by having to optimize for a slightly less performant GPU, and they cut the training cost by roughly 20. It's kind of interesting that something like that can happen. So we just don't know. If you ask what are the fundamental limits of learning given the statistical, meaning the amount of data, and the computational, meaning the amount of compute, CPUs, energy that we put into it, what's the best way of doing it? So we just are far away from that. And this scaling up brings more questions. So there are the scaling laws that are empirically observed. So can we theoretically understand where those exponents come from? And there are also works that show that the capabilities emerge with scale. Like, suddenly you start to be able to translate from one language to another. So are these phase transitions in some proper sense of the word, or what are those? The fact that the parameters that are learnable are many brings the well-known curse of dimensionality, that the search space becomes exponentially large, and so pretty much everywhere there will be computationally hard problems. And we don't understand when actually this computational hardness can be avoided and it can be done efficiently. But there is at least one good thing with the scaling, that it brings also some answers. And that's something that David Donohoe about 20 years ago coined as the blessing of dimensionality. And there's this simple idea that in the right scaling limit, the concentration of measure allows for description in terms of just few order parameters. Now, what I said might sound a bit mysterious, but that's what I said. That's why statistical physics works. And that's what Gibbs realized 130 years ago or so. And he leveraged it to create statistical physics. And anybody here who had at least an undergraduate course of statistical physics is familiar with this blessing of dimensionality, how the randomness stops to matter when the systems are large. And it's also only with large scale that things like phase transitions actually appear. If you had only 100 molecules, there would be no phase transitions. So this gives us a tool that, in this world of scaling that makes things complicated, we have this thread that can do something simple. So what do we do with that? We aim to build a theory that would describe these fundamental limits, starting with simplified models. The real thing is way too complicated. So here I just give you one slide how I think about it. So AI once understood, imagine the Boeing 380, That's kind of a nice, elegant way to travel. And the AI theory is currently more like a paper airplane. So you'll be okay, that's not so good. So why do we do that? Because the AI practice today, I see it a bit like that. I added the brain with a question mark in the bracket for you to tell me whether that's also, evolution kind of made it way that it's not clear that everything that is there is probably not needed, right? So if we were to start over, how would we do it, right? And my kind of premise is that understanding the optimal thing may be much easier than understanding either the biological instantiation of our intelligence or the current instantiation of artificial intelligence that we are working with. Starting with the paper airplane. Okay, that's where we are. So, it flies, it's simpler, room for understanding, but it's not yet a plane. So how, now this is very generic, right? That could be said about any kind of theory in science. So now going to models of learning specifically, what are kind of the key ingredients that the models should not miss? If we miss any of them, we are kind of throwing the baby with the water. The model for the data and the task. And I say a model here because if we don't model the data and the task, we kind of take it from the real world, then it's already very difficult to even describe it. So modeling it for me is the first key ingredient. Then there is the architecture of the network, and then in computer science, the estimator, what we are actually trying to compute, and the algorithm that serves to compute it. Now, why do I kind of put them together and say that they're inseparable? Because if we put aside the algorithm, we may have architectures that are representing the structure of the data, but if it is not computationally efficiently doable, then it's useless. And that's also true in biology. That's not only restricted to artificial learning. If we do not model the data and we are considering any possible data, then we are in a world where we mathematically know that there are NP hard problems, that there are computationally hard problems. So whatever we say cannot be true for all data. So we better assume something about the data so that what we say about it actually may be non-trivial. And then the neural network architecture needs to be somehow linked to the two. It makes the algorithm work, but it captures the right structure of the data. And then the scaling limit, because that seems to be the key kind of thing that is needed here and also allows us to say something. So that's kind of my strategy to go about that, but really in theory of learning, this started a long time ago, and the person that I would cite here, if I should pick one, is Elizabeth Gardner, who kind of long time ago conceptualized a lot of these things just in the right way. So she came up with this, what we call today teacher-student setting, where to start with these models, we just model the data, the inputs as IID Gaussians, and then say the labels that the function that we are then going to learn is created by some teacher neural network that is using random weights. The weights are then not given to the student neural network. What we give to the student neural network are just the examples, and the student of neural network should learn from the examples. And then the question is, how many samples does it need? Does it have efficient algorithms, etc.? And that's what Gardner did in the simplest possible case, where the neural network is just a single layer perceptron, so no hidden units, just inputs, one output, and the labels are created, just making scalar products of the weights times the inputs. In the high dimensional scaling limit, that's really crucial there, and that's something that then computer science and statistics also started doing, but much later than this. So when I go back to my ingredients, that's the kind of simplest case. Single layer neural network. The estimator is just optimally respective of any algorithm so far, and the data are very, very simple. So jumping 30 years forward, what back then Elizabeth Gardner and related works did in a kind of theoretical physics way, since we could establish fully mathematically rigorously to also make the computer science colleagues happy. And the result is a formula, this phi rs of m of a single parameter, that describes for this model what is the best error that we obtain given a number of samples, and also describes the error achieved by a specific algorithm that we call AMP, approximate message passing. So I could show you the formula and the methods, but okay, I will rather refer you to the paper. There is this particular algorithm that I want to say 2 more words about that plays a very special role in kind of our way of analyzing these systems. One nice thing about it, it's very easy to analyze it. So that's kind of rare for learning algorithms that learn on high-dimensional problems, but this one is easy to analyze. And more than that, it's a good proxy for best efficiently achievable accuracy that we can get. It's a particular algorithm, but in a class of problems, it's actually conjectured to be the best among those that run fast. If this was like a mathematical statement, I would be, probably giving talks at some like computer science conferences, because we would be like showing that P is not NP, or solving some like really non-trivial problems. So we are not yet there, but the conjecture seems to stand that this is our proxy for what's efficiently doable. That's a very difficult kind of thing to grasp even in computer science. What is actually, the kind of computational complexity that you may have heard about is about the worst case. That's not very useful when it comes to learning. It's not, the data are not worst case. We want to understand the kind of typical case. So let me rather show you how the result of this theory looks like. And I like this example of a phase retrieval or sign retrieval. So that's actually a problem that comes up in imaging. In any time we image anything with light, we measure the amplitude of the light and not the phase. So that's a very kind of a problem that appears in engineering. And we can formulate it in this teacher-student setting. We have a signal, somehow W star, that we observe through a channel that loses the phase, or sign. So we just take a square of the scalar product. And the data are random, and we observe the labels x, y, and the inputs x, and look at it as a kind of regression problem. So we want to predict new y from new x. We want to learn the function. How are we able to do that? How many samples do we need? So this is, if we now evaluate what the theory tells us, we get a diagram like that, where on the y-axis is how good we are doing. Lower is better, that's the error. And on the x-axis is how many samples we used. So this alpha is the number of samples over the dimension. And we see there 3 kind of interesting places, 3 phase transitions, 2 phase transitions and 1 algorithmic threshold. At half, we start to be able to do better than randomly guessing at alpha half. And that's a second order phase transition, just like the one if we take magnets at something like 700 Celsius, magnets will not, or Kelvin, I forgot which one, a magnet will not be magnetic anymore, it will just fall from the fridge. So that's this type of a phase transition. And then at alpha 1, there is a first order phase transition, so that's the one we are more familiar with. Water has a first order phase transition. It changes its density discontinuously when it evaporates, right? Water, that's true. And here what's happening is, mathematically it's the same thing. So the error jumps discontinuously from something like 50% right to just 0, perfect generalization. But if you look at this algorithm, AMP, that I said is a proxy for what's best possible, it lags a bit behind. There is a phase that is hard, that this algorithm, and we conjecture that no other efficient algorithm will actually be able to learn. So from the point of view of physics, if we make the analogy of the liquid being the phase where we are just randomly guessing, and the ice being the phase where we found something nice, the regular structure, then this hard phase would be the analog of a supercooled liquid, when you actually manage to supercool water to say -5 degrees Celsius and it stays water. If you do it carefully, you can do it. Now with water, this is not like so easy to actually do it, because there is nucleation. It lives in small dimensions, so it actually escapes from this phase. But in the high dimensional problems like the one we are looking at, this metastability survives for exponentially long time, so here is just, there is no way to go around that. So computationally, the first order phase transitions, when they arrive in computational problems, they are related to computational hardness. That is somehow fundamentally unsurmountable, that is unavoidable. So then we kind of end up, this is just one example, but we can analyze this type of phase diagram in dozens of others, and we end up with this kind of phase diagram where if we have few data or few compute or few signal to noise ratio, it's impossible to learn anything. And then in the large size limit, typically sharply, we transition to a phase that is hard to learn, where it's possible if we had exponential time, but hard. And then there is the computational threshold, where the best computational method will manage. And typically, this is not the same where the standard methods are working currently. So then this gives us a nice strategy to kind of take the standard methods and try to push them down to the computational threshold where we know it's still possible. So that's a strategy that actually in other fields of worked very well. For instance, the error correction that is done in your phone in the wireless communication, that's in the 50s when Shannon actually derived what's possible in terms of correcting errors, and then the industry worked for 50 years to actually make it happen, just trying to match the threshold. So this kind of matching the Shannon threshold. So this kind of matching the threshold, that's a very concrete strategy how to actually improve the systems. So if I stick still now with this strategy in mind, if I stick to the phase retrieval, I should, this approximate message passing is a toy algorithm that we like for the reasons I told you, but that's not what machine learning uses. And machine learning uses gradient descent. You just write a loss function. This is still the loss function written for the phase retrieval. And you just go down, you take the gradient, you go step down, you repeat that. So that's the standard method. So how does this standard method work in this toy case of the phase retrieval? So again, this axis is the alpha, the number of samples over the dimension. And compared to the phase transitions we had before for the AMP or the information theoretic, gradient descent lags behind. Like it needs many more samples. So that's kind of the green part of my phase diagram 2 slides back. Okay, so what? So now you would want to bridge that gap. So how do you bridge that gap? So that's something that is interesting because not only deep learning uses gradient descent, but deep learning also uses networks that are highly over-parameterized. What does this buzzword, highly over-parameterized, mean? So if you understood the phase retrieval example that is just a very simple, right, like a teacher-student single layer neural network, over-parameterized means you're changing nothing about how you're generating the data. That's still the same problem, that's still the same toy model, but now you're changing the loss on which you're running the gradient descent. So instead of matching the loss to the teacher, you know the teacher, so it makes sense to kind of match your model to the true nature of the model in all sciences, physics included. But here you don't do that. You actually take your model that has many more hidden units, even if your original data generative process does not have any hidden units. This sounds crazy, but do that and nevertheless, and run the gradient descent on this. And if we do this, and in this particular example, that's something that we can prove, you actually only need twice the dimension to make the gradient descent works. So you see this crazy idea of over-parameterizing, mismatching actually the computational model to the actual way the nature generated your data is advantageous once put together with an algorithmic learning procedure that is suboptimal. So that's like a very interesting concept here that comes out. Okay, so going kind of back to my diagram here, right? Single layer neural network, IID inputs teacher labels, the optimal way or the kind of AMP algorithm as a toy proxy, that's the starting point. Now, over the past 10 years, we have been kind of working on the different 3 directions and making it more interesting. So starting with replacing the algorithm with the gradient descent, or the stochastic gradient descent. Here I just put some references, but intentionally pretty small. If you want, I can send you the slides then. So long line of work on that direction, understanding actually many things. Like how is learning with gradient descent related to the optimal possible learning. On the side of the data, of course, no data interesting ones are IID Gaussian, that's just the starting point. So what if we already add a covariance on the input data? So that seems like not much, but quite interestingly, because of a universality theorem that we call Gaussian equivalence, this actually describes a big class of other learning problems, learning with kernels, with random features. It's able to explain the double descent, tell us more about overparameterization, derive some very simple cases of the scaling laws. Again, many papers, and capture actually real data for very simple networks. This just adding the covariance captures the learning curves of real data. So a lot of work on that side as well in the past years. Now, what about the hidden units? That's kind of the deep learning has many hidden layers. So what is done there? So a line of work where, again, a lot has been understood is the case where you just have few hidden units. So in the limit, as before, number of samples to infinity, dimension to infinity, but just like 5 hidden units. That's called a multi-index model. And there has been, again, dozens of papers on that case and very interesting results happening. If you take more hidden units, I just want to say that's the simplest, so far unsolved case. Unsolved in the sense that, you know, we believe the blessing of dimensionality must kick in some way, and we should be able to write a closed formula describing, you know, the learning curve and the phase transitions, but we don't have it yet. If you know, in the interesting regime of number of samples, which in this case would be quadratic with the dimension, you know, these papers are somehow just describing, look, this is an important open problem and we are not yet there. Okay, but so what, right? Like, who cares about multi-layer perceptrons anyway? Because that's not what ChatGPT does. These large language models that interest everyone today, they use different architectures that are called transformers. And so, you know, can we study that? Let's see. So the ingredients, as said, of the state-of-the-art large language models on the left-hand side, compared to what I talked about previously, or the usual multi-layer perceptron deep learning. So there are two differences that, from my point of view, are very crucial. The first one is that instead of putting a vector for each sample at the input, transformers take a matrix as an input for each sample. So matrix, that is sequence of tokens. So in the language, each token is typically one word, and you represent each word, say, as an 800 dimensional vector. And then the text is the sequence, so each word, 800 dimensional vector, and you have, say, 10,000 words. So this creates a matrix that is 10,000 by 800. And then different samples are different texts. So now, okay, it's not a vector, it's a matrix. So you know, okay, that's a difference. Why, right? Because you could take that matrix and vectorize it from the point of view of like approximation theory, like the kind of mathematics that describes that neural networks are good functions that can represent everything. This should change nothing. There must be something computationally advantageous to doing that, if it is actually advantageous to doing that. And then the way these sequences of vectors are processed is not just by multiplying the vectors by matrices as the fully connected networks do, but there is this layer called the dot product attention. So there are weights as before that are acting on the embedding dimension, that's the dimension to which you map each word. So those are acting similarly as you were having the weights acting in the multi-layer perceptrons. But then how are the different elements from the sequence compared to each other? That is actually through this matrix, that now is a matrix that is the length by length. There is no learnable parameter that would have a dimension of the length. It's all kind of done comparing these kind of keys and queries together. But the key thing here is that this matrix at the input has two dimensions, the embedding dimension and the sequence dimension. You treat the two directions very differently. The way you mix them is very different for the two of them. Okay, so let's put that together. We have our triangle, our kind of systematic way of including what is needed and making it more interesting and more realistic. and the large size limit, in practice, both the embedding dimension and the sequence length are large, something like 1,000, and the sequence length these days can be millions or more. So again, the sequences are everywhere. There's not only the language, but code, proteins. So now, as said, we have 3 indices. This is the sample, this is the position in the sequence, this is the position in the vector in which you embedded your elements. And here, again, what the attention does to it, it separates the way it deals with the mixing of the features in the embedding dimension from the mixing of the tokens among each other. Okay, so the separation between how it deals with the tokens and the embedding is important. So now, given that, why are we processing the data as sequences rather than vectors? Why don't we vectorize them? So that's a very basic and beautiful question. So can we find a synthetic, simple learning task where it's better to actually present the data as sequences and not as vectors? And something that would be as simple as possible as the linear regression is, or the generalized linear regression that I was talking about. Because in the current theory, that's where a lot of things start, like a lot of scaling laws, double descent, overparameterization, all that can be understood already within linear regression or variants of it. So we want to do something like that here. And the only kind of thing that we want on top is that the inputs are sequences, and the latent variables are dealing differently with the 2 dimensions. So what we do, we take a model like this. If this S here was just, unstructured, it would be just linear regression. But we actually take it structured. We make it a product of 2 matrices, where one of the matrices mixes the tokens, and the other matrix mixes the embedding features. We call it the bilinear sequence regression. It's kind of a toy case of what people call in machine learning MLP mixer, that is some variant of a transformer that also does very well on vision tasks, for instance, comparable to transformers. And okay, for a model like that, now our blessing of dimensionality kicks in, all works out. We can write a very nice, simple formula for what's the optimal test error here. And it just comes, for random matrix theory lovers, it's just like free convolution of some nice 2 spectral distributions that gives you this function here, and then everything else here are just constants, like the constants that stem from the limit we are taking, or just like numbers. So then in this model, we can characterize the performance gain with respect to linear regression. So what's the gain we get here from the fact that we are presenting the data as sequences of tokens rather than just vectors? And again, we have phase transitions there, second order phase transition to perfect recovery, and many other things that we can say about this model. So what about the attention? So far in this bilinear sequence regression, I kind of captured the fact that I'm learning from sequences of tokens and made it as simple as possible to be like essentially as simple as linear regression, except that this bilinear regression already, the optimization problem is non-trivial, the gradient descent is non-convex there, and one needs to already work quite hard to actually derive all these results. But there is still the attention. What can we kind of say about that? Kind of going to this side of the triangle. In order to do something there, we actually needed to change a bit the limit to make a model that we can solve. And so we took a limit where the embedding dimension is large, but the sequences won't be so long. So say the length of the sequence will be 10. So that's the price to pay to be able to, so far, analyze the attention layers. And then we write this, if you haven't seen the attention before, this will seem like, okay, that's an impenetrable equation, but if you have seen it, that's the kind of natural model you would write for the teacher that actually uses the attention and has M layers. So M here is the depth, and then this is the attention matrix. There are some skip connections there. That's, the signal is passed through the layer, but there is also a connection to the next layer without actually transforming it in any way. So that's something that is always present in those modern architectures. And what are these key inquiries? Here we actually take them the same. We don't have to, but that makes things simple. And we restrict their rank. So here we restrict their rank to some small number p. Usually their rank is not restricted. That's not such a big restriction of the MAL. But anyway, it's a kind of first MAL that has the attention, is multi-layer. There are these target weights, again, as in the teacher-student, that we use to generate the outputs, but then we hide them, and then we ask whether some learner can actually learn the same function. So now what is interesting about this MAL is the following thing, that we actually we define a different MAL. This actually will be a larger class of MALs that we call sequence multi-index MAL. So now it has a very similar form of what I was showing before. Like for instance, when we talked about the phase retrieval, this f was just a square and I only had like one term here. But here I take L is the sequence length, and P, what P is, I will actually show, or in this paper we show, I will not show it on the slides, it's a bit like technically you need to sit on it, but it's elementary to see that the previous deep attention MAL is just a special case of the sequence multi-index MAL, where the P is just the sum of the ranks of the keys and queries over all the layers. Okay, so if you sit for half an hour, you will see this. In the limit that is as before, but now the length of the sequence and this rank is of order 1. So that's just a realization that, what does this mean? Well, this means that all those dozens of papers that are in the literature on the multi-index MALs and the methodology that people develop there to analyze them, that we can readily transport them to analyze the deep attention. So that's pretty amazing because that's something that we did not know how to do before. So that's what I'm saying here. It's a lens to study the learning dynamics of the multiple attention layers, essentially with the previous tools. That's what we often do in math, right? We just bring it back to something that we know how to study already. So that's what this sequence multi-index MAL does. So to finish, I have just one application of what we actually get when we study this sequence multi-index MAL. Not that study, we will go to just a single layer of attention, but we are looking at something specific here. It's in the paper titled Positional and Semantic Learning. So let me kind of explain where we are getting at this. So very kind of going back to the language, right? The cat likes red apples. You can say the cat likes red balloons. You change the meaning of the word, the semantics of the word. So this is what we call semantics. The word will then be represented by a vector, so it's all what the vector is matters. Or you change the order of the words. You say the apple like red cat. Or apples like red cat, right? You change the meaning of the sentence, but you just reshuffled the words. So this is when the position matters, when the position of the words actually matters for what the sentence actually wants to say. So now we want to model something like that, like how much the position versus the semantics, how do they interplay when we are actually learning from language? So in terms of, making this more specific in terms of the kind of mathematical elements in the architecture, there is this attention matrix that depends on the vectors that represent the words, so that's the xi and xj, and it also depends on their position. The way the position is added to these architectures is you just add some vector to the word that tells you which word in the sentence this actually was. And now this matrix can even more depend on the axis, then we will say that this is semantic learning, or it can more depend on the positions, and then we will say this is positional learning. If I go back to this picture here, this is just some toy task of counting the occurrence of every letter in a sentence, where we see that depending like how exactly we initialize our algorithm, we actually see that on such a simple task there is a purely positional way of learning it, and there is a purely semantic way of learning it. So now we model this within the sequence multi-index model. This is the teacher function. Again, I will not go too much to the details, but there is in the teacher function a part that is positional and a part that is semantic. And then the student function has the form of the single layer dot product attention, the form that is, you know, the key ingredient in the transformers. There is the scaling limit as I was describing. Now we, you know, unravel the replica method if you want, or the blessing of dimensionality, write a closed set of equations that describe the learning. And what we see, just in physics, right, when you study phase transitions in physics, the order parameters kind of appear in the analysis. You don't have to plug them in. They emerge in the analysis if you kind of treat the, you know, manipulate the objects right. And here as well, we kind of unravel this method that we have to solve the problem, and then there are order parameters that pop up the usual way. Now we look at them, what do they actually mean in our setting? And we see that there is one that correlates what is being learned with the positional embedding, so that's a positional order parameter. And there is one that correlates what is being learned with the semantics that was in the teacher. So this is the semantic order parameter. And then as we increase number of samples, we see a first order phase transition from a phase where the semantic order parameter is 0 and the positional is not, to a phase where the positional order parameter is 0 and the semantic is not. So as you have more and more samples, you start learning from the semantics, not from the position. And this is how it corresponds to the test error. So I will stop with that as an example of how kind of now this mapping of attention layers to the multi-index model allows us to, you know, say interesting things about it. So the take home is that we have this, analyzing the fundamental limits of learning in more and more interesting settings, you know, going around this triangle and making the, you know, including still all these three ingredients. If we throw away any of them, we will be throwing away important things, and making them more and more kind of interesting to capture what is observed in practice. And the large size limit is kind of a key thing that at one hand we are explaining or aiming to explain, at the other hand using to actually make the blessing of dimensionality work. So if you see possible connections to neuroscience, please talk to me about it. That's not something that I'm working on, but I'm very happy to learn and get your ideas. So thank you for your attention. This is our group at a beautiful place in an island in the Mediterranean.
Great, we have time for some questions.
Hi, Lenka, thank you for the great talk. I was really curious about finding different order parameters at the end of your talk. And I wanted to ask you if you think there's a limit to how many order parameters you could discover in data, thinking about the fact that in real inputs to neural systems, there can be many relevant degrees of freedom in the world outside you.
Yes, absolutely. Like, this is a great question, right? You kind of discover what you put in the model. Here we model the data, and only thanks to that we kind of have access to this very elegant closed solution that actually makes the order parameters pop up. So that's where one would need to start, kind of. How do the data look like, right? And for instance, the way people are deriving these scaling laws, you say, oh, in my data there are multiple scales, so I will model them as some like power law decay of correlations in the data. And then, no surprise, you have an order parameter that actually will capture that power law decay that we're there to start with in your model for data. So it really goes, so yes, but it really goes back to kind of having the right model for the data. And once you have, then I would say totally yes, if it is kind of, you know, we are making the set of tools that you can use to solve it more powerful and more powerful. So if it meets your model for data, then absolutely. I mean, that's the hope in the future.
Absolutely beautiful talk. I was pretty impressed by the transformer kind of inspired analysis. To what extent do you think this can be carried forward and people can treat with these techniques more realistic transformer-like architectures? And do you think there's any fundamental obstacles to doing this?
Right, so think of the airplane analogy, right? I'm not sure I actually want to carry it through in the more realistic transformers, in the sense that there may be a lot of details that I actually do not want. So how I'm thinking about it rather is, why even the attention layer is so important, right? There are alternatives to how this is done. I mentioned the MLP mixer. There are the state space model, which actually are much closer to recurrent neural networks. So you guys may be kind of more may feel closer to them. Like that's in a sense a different way to deal with the attention, if you want. Like people kind of found, Albert Gu found this nice kind of mapping of all together in one framework. He calls this a matrix mixer, a bit like MLP mixer, but no, the matrices are mixing. So what I'm more hoping is that in the landscape of all possible architectures, this kind of strategy will help us to clear kind of what is needed and what is there and how it's related to the structure of the data, before actually kind of taking like a path that is constrained to whatever the current state of the art is, because this will change in a year anyway. Right? So it's a bit different than with the brain. The brain is here, and we will care about it for still long, right? Because if nothing else, we want to heal people that have problems with their brain. But in the AI landscape, the kind of system that is the most performant is currently changing every roughly year or two, or more, or less. So yes, I'm kind of going after what's the best possible, and maybe jump through the current state of the art. That's one strategy.
Time for a couple more.
Yeah, thank you for this wonderful talk. One of the fascinating wonders of deep learning for me is how they do feature learning, and that's also very fascinating for biological circuits. And from your vast experience on statistical physics, I'd be curious, what are the roadblocks of understanding feature learning, and what are the most promising candidates?
I don't think there are any big roadblocks understanding feature learning. Essentially, already this first line of work of Elizabeth Gardner was around understanding feature learning. I think here it may be a bit of something that happens often in sciences, that at some point, people looked, oh, look, there is this regime in which the neural network is actually just a big kernel, and there is this lazy training, and people presented it as some kind of dichotomy. Either we do this simple thing or we describe feature learning. So to me, we were always kind of going after describing feature learning, and when you ask about the roadblocks, it's essentially the whole talk, right? The one roadblock that I mentioned somewhere in the middle is this extensive width two-layer neural network. If we could do that, we could actually do multi-layer perceptron, and we still can't, right? It's kind of surprising that I showed you we can analyze multi-layer attention, and I can explain how it is different. But I still within this set of methods, to the precision that I would like to have, I still cannot do a three-layer, multi-layer perceptron in an interesting regime. So that's one big roadblock, but we will solve it. It's just maybe not, in the time scale in which research usually works.
Thank you.
Maybe we can do one more question while the speakers switch their...
So thank you for the very nice talk. So I'm wondering, to what extent do features of traditional critical phenomena in physical systems, things like very long-range spatial and temporal correlations and diverging susceptibility and so on, to what extent do those carry over to, or what are the analogs of those things for the types of learning phase transitions that you described?
So the phase transitions that I described, they really are phase transitions in the usual sense. The difference here is that the systems we are describing, they do live in very large dimension. By kind of these A, the real ones seem to, and B, that's where the analysis is simpler. Just like in physics, right? The mean field condensed matter theory is simpler than the three-dimensional condensed matter theory. So That's anyway where we are so far. And you know, you have diverging susceptibilities. That's just the running time of the algorithm. And yeah, it takes longer time to converge if you are close to a second order phase transition. Absolutely, like, you know, all those things come with it because it's the same equations at the end of the day that you're solving. Now, some of these things that, you know, we cherish in physics, like all the renormalization group and things that come because things are low dimensional. That's an interesting question, up to which role this is important here. It would be important in case the data on which it is learning are somehow intrinsically low dimensional. And I'm rather in the other limit so far. It's okay, these are big vectors and I will assume then unstructures, so it's high dimensional. It allows me to do the analysis. It may be, and right, I think this community is kind of champion in thinking about that there are actually some low-dimensional manifolds hidden in the data, and that this is super important, and that it's all about kind of finding those. So if that's the case, then the low dimensionality will start to be important. It will break most of my analysis methods. Okay, that's life. But so this we don't know how much kind of intrinsic low dimensionality there is in language, for instance. It's a really interesting question, and there are works that are showing some evidence towards this. It's not clear yet, but it's a really interesting direction.
Okay, thank you.
Let's thank Lenka again. Now we'll move on to contributed talks. Next is Valentina Njaradi from Gatsby.
Humans and other animals constantly have to decide how best to allocate their cognitive resources to learning. For example, if you're learning how to play the guitar, you have two options at the start. Either you will put in the effort to learn the music theory, practice all of the techniques, or you can just go on YouTube and quickly learn a couple of songs. Have you picked this choice, you might be able to play your songs quicker, but over time you might realize you'll hit a wall when you want to play more complex songs. On the other hand, had you put in the effort to learn these fundamentals in the beginning, you will become a much more versatile musician that can play or even compose complex pieces. This trade-off between putting in the effort to learn something to get greater rewards later, or doing something easy and familiar to get rewards now, is at the very center of cognitive control of learning. Animals face similar trade-offs. If we have a look at rats, who are performing a free response to alternative forced choice task and watch the reward rates progress as they engage with the task, some rats, shown in black, are very impulsive and they make their decisions quickly after seeing the stimuli. Other rats, the ones shown in red, take their time and really contemplate before making any decisions, and this makes them slower in the beginning, causing lower reward rates, but over time they tend to outperform the black rats, because they have put in more effort to learn this and exhibited better cognitive control over learning. Previous research has explored cognitive control over various behaviors, but here we will present you a theory that specifically addresses its role in learning. In our setup, we'll be modeling the animal with a simple linear shallow network, and the network will be performing a task where the aim is to find a decision boundary between two classes. As the network learns this task, its performance will be increasing over time, where the performance depends on the weights of the network and is related to the mean squared error on the task. We can zoom in on the network and watch how its weights progress as they slowly approach the target boundary. Now, the animal might want to learn this as quickly as possible to get rewards as soon as possible, and it can do that by controlling its own learning. While there are many different ways to pick this control, the one we're going to choose for this modeling is going to be learning rate. In this situation, the learning rate was a small fixed number, but the animal could have picked to put in more effort to learn this quickly. But putting in too much effort could cost them energy, effort, or maybe even rewards. So choosing different time-varying controls might be beneficial. The way control will impact their learning dynamics is through a simple gradient ascent equation, where the weight updates will depend both on the control signal and on the gradient of the performance. How much rewards will the network be able to collect throughout this task will depend on two factors. One is performance, where if you perform better, you will get more rewards. And the other one is control, where the more control you put in, the more rewards you will lose. Just like in the rat example, if they were too slow, they were losing some rewards. Here we're explicitly putting this cost of control that is guided by this parameter beta. The instantaneous reward rate is hence a trade-off between these two factors, but our network won't just care about instantaneous reward rates. Rather, it will care about the total amount of rewards it can collect throughout the task, modeled as an integral below this curve. And there will also be a discount factor gamma, similar to reinforcement learning discounted time, that will tell us how much the animal cares about rewards that happen far into the future. Now, if the network decided to put in more effort to learn this and put in more control, it would increase its performance, but in this situation, it might cost them so much that it won't be worth it, and they will collect less rewards than before. Similarly, if you pick to learn faster in the beginning and then slow down later on, you might gain similar performance and mitigate some of these cost issues. But finding what is the optimal control of learning is a really hard problem because it involves maximizing this entire integral with respect to the learning dynamics over an entire space of functions. There are a couple of ways to do this. We have all of those equations. We can just apply numerical methods and get some answers out. But these solutions are often not very interpretable, and in our setup, they will yield open loop or offline control, which would mean that the control is always a predetermined signal ahead of learning that cannot adapt to any real-time progress. A much more powerful approach would be to do analytical methods and find closed-loop solutions that can dynamically adapt to the state of the system. But previous work has either relied on linearity assumptions that don't hold in this case, or on assuming very specific learning curves. There is a third way, though, and it involves solving the Hamilton-Jacobi-Bellman equation that is similar to the Bellman equation from reinforcement learning, and it tells us how the value function for the system behaves. If we were able to solve this function, we would get everything we want. We would get interpretable solutions and closed-loop control, but there is a problem. This doesn't have any known solutions. If you don't believe me, this is how it looks like. It's a nonlinear partial differential equation, and these are just notoriously hard to solve. What we have managed to do in this project is to find analytic approximations for this equation and the control problem using a method from control theory called the homotopy perturbation method. While this is quite mathematically involved, it lets us solve problems like this one and gain real insight into how the optimal control looks like and what behaviors arise from it. So for our setup, after a few pages of algebra, we can get expressions that look like this, that tell us exactly how parameters of the task, like the rate of improvement, cost of effort, time left in the task, or the discount factor, impact the control. If we plot this control over time, we will see that even a low-order approximation, such as this one, will align fairly well with a numerically optimized solution. But if we want to do some more maths, we can get even more precise answers. Now, the equation on the left will also tell us why this curve looks the way it does, and it mainly depends on these two parameters, where initially, throughout learning, you will be rapidly improving on the task, and there will be a lot of time left for you to collect the reward, so the good idea is to just put in a lot of effort to learn it, but over time, as you start plateauing your performance on the task, you should stop putting in this effort. We can go even further than this and tell you how different parameters of the task will impact the total amount of control you should be putting in, where if the cost of effort goes up, the total amount of control should go down. If the discount factor for an animal is very high, meaning that they really care a lot about rewards that happen far into the future, they should also be putting in more control accordingly. We can even say what happens if the task becomes too difficult, where that will cause the rate of improvement to slow down, meaning the total amount of control should also go down. Let's have a look at what behaviors arise when using this optimal control and revisit the rats from the beginning of this talk. In our setup, if we have two networks perform the same task with two different strategies, where one has an optimal control over its own learning, another one has very little control, we obtain very similar reward rate curves to the rats from this task, suggesting that the red rats might have actually been behaving optimally all along, according to our theory. To summarize, We have developed here an analytic theory for nonlinear control of learning problems that gives online control solutions and interpretable answers for first-order approximations. Higher-order approximations will be even more accurate, but will lose some of this interpretability, and finding them can be algebra-intensive. This method is applicable in some specific setups, but while I've only shown you here one such example of learning rate scheduling on a simple one-neuron network, we have expanded this to bigger shallow networks where results look similar, as well as to task attention and semantic development, where we can show what tasks should agents prioritize when learning, which matched patterns observed in children's learning. Finally, we believe that control of learning is not just an auxiliary mechanism, but a fundamental aspect of the learning process itself, especially in biological agents where the two are very deeply intertwined. I would like to thank my collaborators and especially my co-author Rodrigo, and I'm happy to take any questions.
Go ahead.
Hi. Yeah, great talk. I'm wondering if you could talk a little bit about the trade-offs between using this kind of approach for learning rate scheduling versus something like unscented common filtering or extended common filtering to schedule the learning rates.
Yeah, so I guess this approach is rooted with the normative assumption that you're optimizing a total amount of reward during the task. And common filtering uses more different approaches to get at this. I think common filter wouldn't work as well here because it's not a linear control task.
Yeah, but extended and unscented common filters will handle nonlinear systems.
Yeah, but we have tried that, and in these situations, they don't tend to work as well. I think it depends on the level of nonlinearity, I guess, but yeah.
Thanks.
It's really, really cool analysis.
Thank you.
What order correction do you typically need to get good agreement? And do you notice that there are any typical situations where perturbation theory doesn't seem to work that well?
Yeah, so this homotopy perturbation method is one of those that in a particular setup, if it converges, it's going to for sure converge within enough higher approximation orders. The first order approximations are better for just looking at how the shape, I guess, of the control looks like. I wouldn't say it's perfect at predicting exact amounts. We're still working on quantifying all of these results. It's this work in progress, but the higher the approximations that you can compute fairly quickly on a computer could get really close to the numerical answers. Yep.
If there's any more questions, we can take another quick one while the speakers switch laptops.
I was curious if you have any intuition for why learning rate poses a cost. I was not sure why it ends up in the cost function.
Yeah, if we take a very literal approach, it could be just it takes more effort, mental effort to focus really hard and learn something. If we're taking a step back and looking at this as a more abstract thing, if you're a human and you're focusing really hard to do something, you're kind of losing a lot of, I guess, abstract rewards that you could be getting from just doing normal things like exercise and socializing and stuff like that. We think it's more relevant still in biological agents than in networks where such costs don't exist. So we don't propose for this to be a machine learning rate algorithm, but rather just one for biological agents.
Sorry for that. Hi, my name is Matthijs Pals, and I will be presenting our work on inferring stochastic, low-rank recurrent neural networks from neural data. So a general goal in our field is creating models that we can use to understand or interpret neural data. Recurrent neural networks, or RNNs for short, are a popular model class here that we can fit to neural data and then analyze or reverse engineer to get some insight into the underlying neural dynamics. And a particular tractable version of recurrent neural networks are low-rank RNNs. And as I'm using them throughout this talk, I will give you a brief intuition. So let's say we visualize the activity of 3 units in the network. Now we commonly assume in our field that there's some low-dimensional structure in the data, and low-rank RNNs are a way to make this very explicit, as the low-rank connectivity of the network constrains the neural activity to a low-dimensional linear subspace. We can visualize the activity in this low-D subspace, write out the equations for them. So low-rank RNNs really give us a map between the high-dimensional mechanistic description of the RNN in terms of the activity of its units, here on the left, and the low-dimensional latent dynamics on the right. So this makes them particularly attractive as models to be fit to neural data and then analyzed. But typical methods for fitting RNNs to neural data consider deterministic variants, often fitted to trial average data. If you want models that can accurately generate realistic neural data, we need to deal with stochasticity in a principled way. At the same time, there is a large body of work that's concerned with this, that fits probabilistic latent variable models to noisy single trial neural data. But such methods don't always have an obvious mechanistic interpretation. Our main contribution is combining these two approaches. We fit interpretable stochastic low-rank RNNs to neural data with variational inference. This allows us to obtain models that are both interpretable and that can generate long sequences of realistic neural data. So how are we going to do this? For this, we will use a variational inference setup where we predict the distribution over latents given the observed data. We can then decode this back to the original data with an observation model that we can flexibly adjust based on the data modality. Since we have time series data, we learn a sequence over latents. We will also learn the distribution of the latent at the current time step given the previous, and this will be given by the low-rank RNN. We can learn this end to end. There are 2 additional tricks to make this work well. For one, the encoding model will be defined as the low-rank RNN's dynamics updated with the observations. For this, we can use the Kalman update step if observations are Gaussian and linear, or else we will just learn an encoding network to do this. Secondly, we will resample latent trajectories that become unlikely, and we end up with a method that's called variational particle filtering, or variational sequential Monte Carlo. So does this work well? Let's start with some setting with simulated data, where we know the underlying ground truth dynamics. So here's some example data generated by a rank 2 RNN, that's just a noisy oscillator. And now we will use our method to fit a second RNN to the activity of the first. We find that the fit model is a close match to the teacher, and I want to stress that we don't expect time-step-wise correspondence, as we are plotting 2 samples from 2 stochastic models, but rather the distribution over samples should match closely, and this we verified numerically. We repeated this experiment with Poisson observations, and again we find a good match. So the method works well on simulated data, but how about more complicated real-world data sets? I'll show you 3 examples. In the first example, we use data from macaques that are making reaching movements. And we fit a recurrent neural network to spiking activity of the macaque, and we also condition the RNN on the target reaching positions. We can find that we can generate realistic spiking data for the different reaching conditions. But are the underlying latent dynamics also interpretable? We here fit a rank 5 RNN, so let's look at a 5-dimensional latent space of the model. We can first look at the latents inferred by our variational inference setup, and we can see that the latents clearly reflect properties of the macaque's behavior, such as the intended reach target before the reach, as well as the movement during the reaching period. We can also decode the reaches that the macaque makes from the inferred data. Now let's look at samples generated by simulating the RNN. We can see at first a close match between the inferred latents, but since it's a generative model, we can also ask it to generate latents for conditions that were not in the original data set. And we can see that the model allows for realistic interpolation, such as to the reaching movement downwards. In the second example, we fit rank 3 RNNs to spiking data of rodents that are foraging for food and water. We can generate tens of thousands of time steps of realistic neural data, and the model ends up using latent dynamics that closely reflect the underlying local field potential that was not used during training. Now again, don't look for a time step-wise correspondence as it samples from a stochastic model, but distribute like statistics such as the power spectra match between the latent dynamics and the local field potential. And in the final real-world example, we fit low-rank RNNs to 1 minute of baseline EEG data, and we can again find realistic generation. Here, we compare to state-of-the-art methods for fitting deterministic models to neural data, and we find that our model allows for lower dimensional latent dynamics, which we hypothesize is because deterministic methods need high-dimensional chaotic dynamics to get variability in the data, whereas we can get by with simpler dynamics plus stochasticity. So to summarize, we fit low-rank RNNs with variational inference. We obtain generative models that we can use to generate long sequences of realistic neural data. You can find most of these results in our recent NERVS publication. There we also look at how to analyze the fit models. In particular, one might be interested in finding all the fixed points of the models. It has previously been shown that if models are piecewise linear, meaning that they, for instance, have ReLU activations, one can find all the fixed points analytically. And the idea is that a unit with ReLU activation splits the phase space into 2 regions, below and before its firing rate threshold. If we had n units, the phase space would be split into 2 to the power n regions, and each of those regions corresponds to a linear dynamical system in which we could solve for the corresponding fixed point. But of course, this is very infeasible with networks of n is hundreds of units. What we also show is that if the networks are additionally low rank, only a small subset of those 2 to the power n regions can contain fixed points, allowing us to reduce the cost of finding all fixed points from exponential number of units to polynomial. And finally, I would like to mention that we are using our method to investigate sequence working memory during of humans, using data from another recent publication, where we already showed that task-trained RNNs can qualitatively match representations in single units of humans during sequence working memory. We now hope to use our new method to get both a quantitative fit as well as to get a window into the population dynamics during working memory. With that, I want to thank all my collaborators and co-authors. I want to thank our funding sources. And I want to mention my PI, Jakob Macke, is looking for people. So if you're interested, check out the website. And if you're interested in this particular project, check out our GitHub or paper. With that, thanks all for listening.
We're a little bit behind now, but maybe time for a couple quick questions.
Hi, thanks for the talk. One quick question. Because you fit in spikes, they might have things like bursts, refractory periods and the like. Is that part of the model? Or like, especially if you look at LFP or other spectral comparisons, do you need to put it in or does it arise?
Hi, so since we have, like for spikes, we so far always assume Poisson observations. So there's nothing like a refractory period because the spikes are sampled independently. There's another work from our group called LDNS, where they actually add some additional mechanism on the observations to get some kind of refractory period. So it could be added to this as well, I think, but it's not part of our current model. Yeah, thanks.
Great, thank you for your talk. In the data where you generated it from an RNN and then matched it, did your inferred RNN match the weights of the generated one? And if so, then how, this was a two-dimensional case, how complicated can the data be to have a good match between inferred and the ground truth?
Excellent question. So I haven't actually looked at the weights that much. I'm not sure if there probably is some redundancy, at least up till some linear transformation, but maybe, I don't know. I haven't looked at it, so I wouldn't know. Would be interesting to check. Yeah.
One more quick one.
Yeah, thank you for the great talk here. So this might completely be my misunderstanding, but to me it sounds like you have two different mechanisms for enforcing low dimensionality in your dynamics. One is through the low dimensional latent variables, and then on top of that you have the low rank RNNs. So I was wondering if you have any thoughts on how these two are interacting with each other, and in principle you could just have like a lower dimensional latent variable model that has like a complete kind of full rank RNN that governs its nonlinearity. So yeah, I was wondering if you have any thoughts on how these two are kind of like interacting with each other.
Yeah, maybe I'm not entirely sure if you understood your question correctly. So what we fit is really this latent dynamics.
Yeah.
This is the latent dynamical system that we fit. So we kind of during fitting, we don't really treat it as an RNN. We fit this low dimensional system, but then afterwards we can always map back to the high dimensional RNN.
Right, but then Z is lower dimensional than X, and then on top of that you have the dynamics of Z governed by a low rank RNN, right?
So what's the question?
Yeah, we can take it offline, sorry.
Yeah, okay, let's maybe discuss after in the break
cool.
now.
Yeah, great, thank you.
Yeah. Let's thank all the speakers.
I have a quick announcement. As you remember, now we have a Shanahan Foundation coffee break, and we have two Shanahan fellows right around here. Could you please stand up? Denise and Anna Mika. They are working at Allen Institute as Shanahan Fellow. So you can meet them in the coffee break area, maybe in the corner closer to the conference meeting room, and you can ask questions about Allen Institute, Shanahan Foundation, the fellowship, like science, any questions you may have. Thank you.